So now we're going to be starting into the second part of Unit 10, which is really the sound portion, Chapter 14. So we'll talk about, what does it mean to be a sound wave? We'll get into talking about beating, kind of how standing sound waves, occur for open and closed tubes. We'll talk about the Doppler effect a bit and kind of the human perception of sound. Sound is a wave that travels through a medium, such as kind of air or some other gas, that can be perceived by our auditory sense. So it means our ears basically can sense it. And sound is a characteristic common to all waves, basically means that it's going to have frequency, period, wavelength, and wave speed. Now the type of wave that we have is a longitudinal wave. So it's going to be these areas of compression and expansion. So with gases, that expansion is known as rarefication. Compression and rarefication of the gases that basically causes the sound wave to form. Traveling through the medium, but it's not like all the particles are moving. It's just those rarefications are those areas where the particles are further apart, and then you get areas where they're compressed. But those compressions kind of travel along, compressing the next bit of gases and then expanding for the next bit of gases that allow those density changes to pass along the wave's energy. Okay. Now we can actually measure these, areas of, higher pressure, lower pressure, the compressions and rarefications, using a microphone. So if I took a microphone, hooked it up to something called an oscilloscope, I could see the waveforms from a sound source. Kind of like having a wave on a string for a standing wave. The speed of sound is determined by the properties of the medium. So air, for example, under standard temperature, 70-degree Fahrenheit air, so 20 degrees Celsius air, standard pressure, is that specifics for the medium would have about a speed of 343 meters per second. Colder air is only as high as about 331. So if we heat the air, the molecules go a little faster, and it basically changes the speed aspect of the air with respect to temperature. Now, like I said, the speed of sound depends on the medium it's moving through. So if we're in water, water is not compressible. It's much denser than air. So we're going to travel 4 times faster than air. In general, then, sound will also travel faster in a solid than it does a liquid. So that's one of the reasons, if you look at the old Westerns, they put their head to the ground to try to hear the oncoming, stampede or the oncoming train, is because the sound waves will travel faster through the solid. And just like any other wave, the speed of that wave is equal to the wavelength times the frequency. So basically, all those frequencies that we can hear are in a set range. We can only hear as low as 20 hertz and as high as 20,000 hertz. But all the waves travel at the same speed. They all travel at, for room temperature, 343 meters per second. As I said, there's that set range that we can hear, about 20 hertz to 20,000 hertz. As you get older, you start to lose some hearing. If you damage your hearing, so those of you who put the earbuds in and crank it up to 11, you're going to damage that range of hearing. You might not hear as high as 20,000 hertz. You might not hear as low as 20 hertz. So any sound that is less than 20 hertz is referred to as infrasonic sound. Any sound that's above 20,000 hertz is called ultrasonic sound. So some animals can hear infrasonic sound. So like elephants, they've been proven to hear as low as 10 to 15 hertz. Bats and dolphins use echolocation, so they use sounds that are above 20,000 hertz to detect things. Humans have actually found uses of those ultrasonic sounds to create basically what we call an ultrasound. We can use it for imaging within the human body. You can find tumors, you can find babies, all in the fact that those sound waves will go out and they will reflect off of or echo off of different tissues within the body. And you can then use that timing difference to map out what's actually there. So now, another interesting thing we talked about was the idea that waves can interfere and interact. So if we have two different waves of two different frequencies and they interact, sometimes part of the wave will interact constructively, other times it'll act destructively. And this will create something known as beating. So you'll actually get areas where the sound will start to get stronger and then weaker, stronger and then weaker. So we define beat frequencies as being the absolute value of the difference of two frequencies. So if I have, say, a 10 hertz sound and an 8 hertz sound, so 10 and 8, the beat frequency there would be 2 hertz. Obviously, we wouldn't hear 10 and 8, but let's say we had something else. Say we had like a 500 hertz sound and a 502 hertz sound. Okay, I would hear a beating of about 2 hertz. So it would make this kind of warbling effect of 2 hertz. Even though my ears can't detect 2 hertz of sound, below 20, I would hear the loudening and softening in a 2 hertz kind of frequency. So now standing sound waves. So standing waves, we already talked about, generally are produced by having one node, at one end, one node at the other. But for columns of air, we actually have to hear the antinode moving. So we have, open tubes and closed tubes. And depending on that, we have to have nodes at certain places and antinodes at certain places. So generally at an open end, we have to have an antinode. So for the first kind of piece, the closed tube, we blow air across the closed tube, so like a soda bottle or like the pipe of a pan flute. We have to form a node at the closed end and an antinode at the open end. Well, if I'm looking at that length, that means in that length, I'm only getting a quarter of the wavelength to produce that first harmonic, or that fundamental frequency. So that tells me then that lambda, the wavelength, is equal to 4 times that length. So if I have a 10 centimeter tube that I'm closed off at one end, the actual wavelength would be 4 times that. It would be 40 centimeters. Okay? If I go through the idea of V equals, F lambda or lambda F, and solve for F, that fundamental frequency would become V over 4L to tell me what that fundamental frequency is of that tube. Now, the interesting part for the closed tube becomes from the fact that I have to have an antinode at the open end and a node at the other end. Because you'd think, well, if I had a quarter, I'd just go up to a half next, all right, to like a second harmonic. Well, I can't hear the second harmonic because the second harmonic would have the node at the open end, which would mean no air is moving out of the tube. I never would hear it. So the next time I'm going to hear it is at the third harmonic, when I get the antinode again at the open end. So we go now that, lambda is now equal to 4/3 of L. And again go through the math, and this time I find out that 3 times that fundamental frequency is what I have. So it's 3 times V over the 4L. And we follow this pattern, and I find out the fundamental frequency was V over 4L, and that any of the harmonics that I produce are n integers of that fundamental. But I can only hear the odd ones. I can only hear 1, 3, 5, 7, 9, ... I would never hear the even harmonics because of that whole issue with you can't have a node at the open end. You can only have an antinode at the open end. So now we get to the open tube. So both ends of the tube are open. So now I'd have to have an antinode, the node somewhere in the middle, and then another antinode at the other end. So now within that length, I get a full half of a wavelength in, not a quarter, but a half wavelength in. So then if I follow that pattern, I go up to the second harmonic, no problem. I get a full wavelength in, a half plus a half is a whole. Third harmonic, I get 3/2 of a wavelength in. And we kind of keep following that pattern. So for the open tube, I can get first, second, third, fourth, all the harmonics. So F1 here would be V over 2L, okay, because the wavelength is twice the length. And again, I follow through and I find that Fn would be equal to N times F1 or N times V over 2L, where again, N can be any harmonic, 1, 2, 3, 4, 5, any integer harmonic. So now we get to the Doppler effect. So the Doppler effect, almost all of you have probably experienced at some point in your life. Whether it's, you're approaching a parked, emergency vehicle that's siren on, or that emergency siren is coming towards you or away from you, you'll hear this shift in frequency or the shift in pitch. Because for sound, we consider frequency to be known as pitch. And when that source of the sound moves towards you as the observer, either or towards you or away from you, or whether you as the observer move towards the source or away from the source, there's a change in the pitch. Now, Doppler doesn't just have to be for sound. It can be for any type of wave where there's a movement towards or away from the source, or movement of the source towards or away from the observer. So examples of this that we use on a more regular basis are Doppler radar. We actually send out radar signals into, weather patterns, clouds, and try to detect the motion within those clouds of the rain and all the stuff in the atmosphere. Another example gets into this thing called redshift and blue shift. So with stars, we know from chemistry that a certain star, when it excites its energy states, should produce a certain color of light. But sometimes when I observe that color of light, the light is either shifted towards the red end of the spectrum or the blue end of the spectrum. So if it's moving away from Earth, the light shifts more towards the red end of the spectrum. If it's moving towards Earth, it moves towards the blue shift in the color spectrum. For like a vehicle, if a vehicle is just stationary, honk on the horn, you're stationary, you're going to hear whatever frequency the horn's making. So it's 1,000 hertz horn, it makes 1,000 hertz. But what happens if the source is moving is on the front side of that source, the wavelengths are getting shorter. So if the wavelength goes down, the frequency goes up, and you hear a higher pitched frequency as it approaches. After it passes you, or if you're on the back side of the source, the wavelengths get longer. And as wavelength goes up, frequency goes down. So you hear a deeper pitched sound. So now there's kind of two separated equations generally presented on this. One for the kind of observer stationary and one for the source stationary. So you've got the whole idea that the frequency you'll observe is the frequency of the source divided by 1 plus minus the source over the sound, and they talk about moving and towards, or the other case where it's the observer that's moving and not the source, it's the f of the source 1 plus minus the observer over the sound, where it's towards and away. Now if you notice, there's a little difference here in the away and the towards. Now I always found this confusing, and a lot of textbooks also recombine this into one big equation, which is what I like to do. But when I do that, I like to specify a little bit of a flip here in this plus minus, which I'll show on the equation sheet when we do it. And the reason I do that is to make sure that you understand that one side will be kind of to remind you it's the towards, one side to remind you it's the away. So the human perception of sound. So how do we actually perceive sound? Well, there's pressure changes in the air, which is carrying energy, and that energy is traveling with time. So energy over time is power. But that power is over a certain area. There's a certain area that's going to be over, and power over area we know is intensity. Or we talk about energy over time over area as intensity when we talk about things like gravity and all that. So we have intensity of sound. So examples of intensity in watts per meter, because power is in watts, area is in meters squared, would be things like, what can rupture your eardrum? Well, 10 to the 4th watts per meter squared could rupture your eardrum. That's like beyond causing pain. That's like actual blood coming out of your ears. Being at a loud rock concert, 10 to the negative 1 watts per meter squared. And we go down there to, a conversation is about 10 to the negative 6. Just you breathing is 10 to the negative 11. And the true threshold of human hearing, if you don't have damaged hearing, is 10 to the negative 12th watts per meter squared. That's a very big difference in energy between the loudest sounds that like cause damage and just being able to hear. You can actually get sounds that are so loud they can actually kill you, never mind just rupture eardrums. Within the sound piece, we need to realize that sound kind of goes out in the area of a sphere because it radiates outward in all directions. Kind of just like light does, or gravity did, or E&M waves kind of do. So we end up with this intensity with kind of that 1 over r squared relationship, so that inverse squared law that we already got used to using with gravity, or with like electrostatic charges. So if I go through the math here and I get a little example done out, if I doubled the distance away, I'd only have a quarter of the intensity. If I was to triple the distance away, I'd have a 1/9 of the intensity. If I go up by quadruple 4 times away, I'd only have 1/16 of the intensity. It kind of keeps dropping off again, that 1 over r squared relationship with the intensity change. So our hearing is actually very versatile and very sensitive. We can detect very, very faint sounds and very, very loud sounds. A faint sound would be like 10 to that negative 11th. That's like, that very faint whisper, the breathing sounds. To put that in perspective, that's like 10 to the negative 1 meters of movement, or 10 to the negative 10 meters of movement, of air molecules. Okay, it's roughly the diameter of an atom. So we're able to detect like atoms moving with like the sensitivity of our hearing. But now, our perception of sound is kind of a little bit interesting, because what we perceive as being twice as loud is actually an intensity change of a factor of 10. So all of our stuff is kind of based on this increasing powers of 10. And that's where Alexander Graham Bell started realizing that things had to get logarithmic for us. So Alexander Graham Bell actually originally came out with the first unit known as the bell. But he realized it was actually really too loud to discuss human hearing, so he reduced it by a factor of 10 again to become the decibel, or a tenth of a bell. So on the decibel scale, the faintest sound you can hear is actually 0 decibels. So if we kind of double the loudness of a sound, we're actually increasing the intensity by a factor of 10. But if we were to double the intensity, we're only increasing the loudness by a factor of 3 decibels. All right. So the smallest kind of increase that we can detect is 1 decibel increase, and that's not doubling the intensity. That's a fraction of that. And to put this in in the scale, mathematically, what a decibel is 10 times the log of the intensity that you're detecting divided by that threshold of human hearing, that 10 to the negative 12 watts per meter squared threshold. A decibel value of about 120 decibels starts to actually cause you physical pain. Around 160 decibels, that's when your eardrums rupture. Above 160, you can actually cause so much, internal damage that you can actually die from being near sounds that loud. Now, another interesting thing about the human ear is that there's actually certain frequencies we're more sensitive to. And that's because we need to think about the fact that our ear canal is basically like a closed tube instrument. So that means there's certain sounds that want to resonate in that tube, but there's also certain sounds that aren't going to, resonate well in that tube. So for certain frequencies, we kind of get these drop-offs. And also, depending on the intensity level in decibels, the drop-offs vary. So we notice here they actually make a note here of what they call the first harmonic of the ear canal. So somewhere here, a little less than 10,000 hertz, is where that first harmonic of the ear canal occurs, and we get a dip in the sensitivity in our hearing. But if you notice, there's a range of kind of the conversational speech of where it lands in terms of frequencies, and it just so happens that the human voice has adapted, or either our ears have adapted to the human voice in such a way that what we hear is in that optimal range.